Hello, everyone. Welcome to today's Quantum Spacetime seminar. We are very happy to have Hong Liu from MIT, who will tell us about emergent times in holography. Over to you, Hong.
Okay, great. Yeah, thanks for the invitation. Yes, I will be talking about some recent work with my student Sam Dusser. So this appeared in two papers. One is a short summary, and then there's a much longer paper. So whenever people start talking about quantum gravity, then we immediately encounter this issue of problem of time, because in quantum mechanics, the time plays a very special role. Essentially, it's an absolute quantity. But in gravity, most of the time is meaningless, because time just a coordinate. It can be changed by arbitrary gauge diffeomorphism transformations. Say, in particular, for example, when you do canonical quantization, your Hamiltonian is essentially zero, means there's no time. When I say most of the time, because in some cases, actually there is actually a asymptotic absolute time. That happens, for example, in ADS. So in ADS, there's an absolute asymptotic time. So because in ADS, there's a boundary. And so the gauge diffeomorphism, they by definition, they go to zero when you approach approaching the boundary. So the asymptotic time is invariant under this gauge time reparametrization, and so this time is actually absolute. Of course, this underlies the ADS-CFT, because this is exactly the time which is due to the boundary time, and this is also the reason the quantum gravity in space-times of other asymptotics appears much more difficult, because there's not the obvious candidate for such absolute asymptotic time. So even when we go back to ADS, to think about ADS-CFT, we can ask the question whether this asymptotic time is sensibly extended to the interior. Okay. So this question is much more non-trivial, because in the interior you do, then the time does become just a coordinate, can be arbitrarily changed. But if the state we are considering have special symmetries, for example, if the corresponding box space-time, if the state is static, and then the corresponding box space-time is time translation invariant, and then there's indeed the preferred time slice in the box, and so in the sense you can extend this time to the interior. But in general situations, when you have general time dependent case, so this is far from being clear. Okay. So it's interesting to consider some case in between these two cases, and so this is provided by the example of internal black hole. So internal black hole, as we know very well, in ADS is supposed to be dual to two copies of the CFT in the thermal field double state. Okay, so there's no interaction between the CFT, but they're in the entangled state. So this internal black hole has time-like Killing vector outside the horizon. Okay, so I show this L and R, F and P regions. So outside the even horizon, which is this -9, and there's a time-like Killing vector, which essentially can be considered as the extension of the boundary time of your asymptotic time to the interior. Okay, so because there's a time-like Killing vector outside the horizon, so essentially you can sensibly extend your asymptotic time to the interior, to this R region and the left region. Okay. But there's not a global time-like Killing vector, because this time stops at the even horizon. And for example, in the F region, there's no such global Killing vector, and in the F and the P region. Okay. So this example can be considered as intermediate before these two cases we mentioned earlier. So here you can extend this boundary, this asymptotic time to part of your space-time. Okay, so this part of the space-time outside the horizon, we can just now use standard ADS-CFT dictionary and relatively straightforwardly. But then we can then try to ask the question: what happens, or how should we understand this F and P region? Okay. And of course, the presence of this F and P region present many mysteries over many years. For example, just how to interpret them, even from the boundary theory. Okay, there have been debates whether the boundary theory could even describe, say, physics in the F and P regions. And also, how do we understand the Kruskal-like time from the boundary? Okay, so in order to understand this F and P regions, it's just not enough to consider the Schwarzschild time. You have to consider some kind of Kruskal-like time, so that you can go into the those regions. And also, how do we understand that somehow this boundary's time stops at the horizon, and actually there is a sharp even horizon in the classical geometry and the associated causal structure. Okay. And also, it's possible, even though there's no interaction between the L and R CFTs, but actually it's possible for observers or for some quanta, which originally from the right, say, region and from the left region, they fall into the black hole and interact with each other in the future region. Okay. And how does that come about? Okay. So we will try to shed some light on those questions. Okay. So before doing that, let me just quickly mention our current understanding of boundary descriptions of Bach evolutions. So the simplest case is the to evolve by HR. So suppose HR is the Hamiltonian for the right CFT, and HL is for the left CFT. So the simplest way to understand the Bach time evolution is to evolve by this HR minus HL. And then this is corresponding to the standard Schwarzschild time evolution on the gravity side, and then give you this kind of time slice. Okay, so if you start with t equal to 0 and evolve with some finite t, then you go to this slice. So for all time, you always stay outside the horizon. Okay. And another possibility is to consider HR plus HL. Okay, so heuristically, HR plus HL generates a time evolution like this. Okay, so a time slice, take the right region going this way and the left region going this way. But I want to emphasize just naive action of this HR plus HL is actually singular at the horizon, which there's some kind of kink here. Okay. Anyway, again, this evolution still does not take you behind the horizon. Okay. So if you want to have some kind of evolution which give you a Cauchy slice, start with the t equal to 0 slice, and go to some other Cauchy slice, which actually cross the horizon, go into the interior, say this F region. And you have to have something more non-trivial. Okay. So the basic idea is that this time somehow should be emergent. Okay. It's not something that you can directly construct out of HR or HL. So the goal, of my talk is to show how to do explicit boundary constructions of Kruskal-like evolutions. Okay, so we would like to understand this kind of emergent time, and also we would like to understand the boundary emergence of horizon and associated causal structure. So here's my plan. So first I will outline the main results, and then I will scale back a little bit to talk about the entanglement structure, say, of relativistic quantum field theory, which actually a main structure there is so-called the type 1 von Neumann algebra. And that can be used as an important hint for us to see how to generate in particular, the associated structure with this type 3 one Neumann algebra is so-called the half-sided modular inclusion or translations. So this will give us important hints how to actually generate this emergent time for the black hole geometry. Okay, and then I will talk about the construction of this cross-cut time like evolutions from boundary, and then finally end with some discussions. So before I continue, do you have any questions?
Yeah, Hong, maybe I can make a comment. So
okay.
In case of ADS3, so you know that there are these metrics introduced by Banyados in the context of Euclidean ADS3, which were like the the finite versions of the Brown-Hainaut deformations, which could be taken all the way inside. Okay, but of course it's Euclidean. Sorry, I meant Euclidean BTZ. So it stopped, at the horizon. So you could do these constructions, but it is possible to generalize these constructions to Lorentzian using Eddington-Finkelstein coordinate system, so that you have some conformal transformations at the boundary, arbitrary conformal transformations, not HR minus HL or HR plus HL, but these are arbitrary conformal transformations at the right boundary as well as the left boundary. And using Eddington-Finkelstein coordinates, actually you can go inside because these are smooth coordinates at the, but of course, these metrics are not unique. One could, somebody else could, invent some other coordinate system, which differs from the one that I'm talking about by a small diffeomorphism. But so this is something that we have done. It is possible to do this, except that these are not unique. So I just wanted to make this comment. Whether, yeah. So
okay.
This is something that we can discuss later offline.
Good. Okay. Yeah. I would like to know in more detail the construction. Yeah, maybe one comment I can make now is two questions. So the first question is that whether you use, say, the Eddington-Finkelstein as an input, because one goal of this construction is really to see how to see the emerges from the boundary without using such kind of bark coordinate as an input. And so this is one aspect. And another aspect, another goal is that to really construct this kind of emergent time in the diffeomorphism invariant way. Because in the bark, any kind of construction, you use any coordinate, somehow you have the issue that it's not, as you mentioned, it's a coordinate choice. And so you suspect that somehow should correspond to, there should be some diffeomorphism invariant construction behind it, but you work with some specific coordinates. And so our goal is actually, when you can do this intrinsically from the boundary theory, then there will be intrinsic diffeomorphism invariants. We're not dependent on any coordinate choice, etc. Yeah.
I see. Got it. Okay. Thank you.
Okay. Good. Yeah.
So, sorry, Hong, can I ask a question? Maybe it's a similar lines. Of course, I know you pursue a very deep approach to this question, but just simple-mindedly, could I say that partly the problem we're trying to go inside the horizon is that, as you said, we have a very precise map between bulk and boundary time, Schwarzschild time outside the horizon, but we don't have a precise map for the radial coordinate. I mean, intuitively, it's the RG scale, but it's not a very precise thing. If there was a precise map, then admittedly using the bulk, we could do the coordinate transformation between Schwarzschild time and R to Kruskal on the boundary and see. But I guess there isn't such a precise map. I just wanted to ask you what you thought about that. Sorry.
Yeah, that's a very good. That's a very good point. Indeed. So again, just any kind of coordinate choice in the bulk, would be, so somehow to translate, you see, we can define, say we can define a bulk operator in the right region, in a reasonable, straightforward way. Say by shooting some, you can define it in the diffeomorphism invariant way by shooting geodesics, and by shooting geodesics from the boundary, and then you can define, at least you can define some kind of bulk operator, say in the right region and in the left region, with the help of the boundary time, and to define such things. And but to translate the whole thing into geometry in the bulk, and then to be able to perform coordinate transformation, that's not the level we have right now. It's not clear how we really to do that kind of thing.
Okay, thank you.
Okay, indeed, as I will say later, what we will do is that we will assume the ADS-CFT for the right and the left region, just following from the standard ADS-CFT dictionary, and then try to construct from the boundary theory the F and P region. Okay, so our input is this. Suppose we already know how to say reconstruct the bulk region from the right. Good. So let me just first outline the main results, and so we will show that there exist evolution operators on the boundary, which say of the following form. Say there's some generator G, and then you can consider the one parameter group generated by this Hermitian operator G, and this G have the following properties. Say this involves both R and L degrees freedom in a highly non-trivial way, and G is bounded from below. Okay, in the sense that G behaves like a Hamiltonian, is bounded from below. And in particular, we can act, say, an operator in the right region. Say, let's take a point in the right region, and we know, say, our input is that we know how to reconstruct this operator from the boundary theory. Okay, so this just follows from standard ADS-CFT dictionary applied to the right region, and then now you can just treat this as a boundary operator, and then you can now act by this boundary evolution operator US. And now the claim is that this evolved operator can take you inside the horizon for sufficiently large S. Okay, and in particular, we will see a sharp signature of the horizon. And in the sense, such kind of evolution actually generates this future and past region from the right and L region. Okay. Good. So let me just emphasize that so we can interpret, say, this S then as an infalling time. Okay, and then this G can be considered as a Hamiltonian, which evolve you, say, take you into some other Cauchy slice which cross the horizon. Okay. So for the BTZ case, so we have a general procedure to do this kind of construction, but for BTZ you can actually work it out, some examples explicitly. Okay, and I should mention there are also infinite number of such kind of evolution operator you can construct, and so I will only be describing the simplest one. Okay. So again, let's just imagine you start the operator in the right region, and this belongs to the right CFT. Okay, and then you evolve with this operator. And then such, it turns out that the evolution have the following properties. It said you find, say, let's take S equal to 0 would be the identity. Then let's consider take S greater than 0. It turns out that there is a finite value S0 that for S smaller than S0, this operator just remain in the right CFT. But then at this critical value S0, when you cross it, and then suddenly this revolution will contain a part, including the left CFT. Okay. So we claim this is the signature of a sharp horizon. Okay. And indeed, this is what you expect. So if you geometrically start with the operator in the right region, and if you evolve it across the horizon, so before you cross the horizon, it's in the right region and then belongs to the right CFT. But once it crosses the horizon, and then it becomes causally connected with the left region, and then it will have to involve left CFT left degree freedom. Okay, so we just interpret. Yeah, so this is purely an algebraic statement you can do in the field theory, and so we interpret it as a signature of a sharp horizon. So in fact, you can actually generalize this notion. Okay, we can consider two quantum systems. Say not necessarily those system with a gravity dual or with a long gravity dual. Say we can consider thermal field double states, and if we such a US and S0 exist, and we can say they are causally connectable in the sense that we can say if there's a dual geometry, then the dual geometry should involve some kind of sharp horizon. Okay. So now let me say a little bit about the geometric interpretation of this S0. So this is S0 is a purely boundary quantity. Okay, but it turns out that this actually have a geometric interpretation in the bulk. So it turns out, say let me just draw a simplified the Kruskal diagram, and this U and V are Kruskal coordinates, and these two axes are the location of the event horizon. And let's imagine you start the operator at the point in the right region, say with initial Kruskal coordinate U0 and V0. And then it turns out that this critical S0, which takes this point, say behind the horizon to have this structure involving the left CFT. So this S0 turns out to be exactly the minus the value for the Kruskal coordinates U0. So it precisely is a null distance to the horizon, say along this U axis. Okay. So for this for some particular choice of this US. Okay. And in particular, say if you choose this point to be close to the horizon, and turns out that this transformation is actually just a local transformation. It's just corresponding to a Kruskal law translation. Okay. But if you are at the general points, and actually transformation is non-local, but it's non-local, but in a way which respects the causal structure. Okay, respect the causal structure in the following way. Okay, so we can consider more refined question. So let's consider, say you start with an operator in the right region. And then now let's consider another operator in the left region. Again, the U and the V axis are the event horizon. So now let's look at this commutator. So this evolved the right operator by S and the commutator with this left operator. In order for this commutator to be non-zero, so this evolved operator have to fall into the light cone, okay, of this X2, okay. And again, the minimal null distance from this point to enter the light cone of this X2 is a U1 plus U2. Okay, a U1 is the Kruskal coordinate for this X1, and U2 is a Korsakoff coordinate, U Korsakoff coordinate for x2. And so when S is smaller than this value, and then you find that the commutator is 0. But for S is greater than this value, you find the commutator is non-zero. So even though the evolution of this phi r xy is non-local, okay, but still somehow this non-locality respects, despite this non-local evolution, there's a sharp causal structure you can see from here. Okay.
I see. So, sorry, Hong, can I ask you a question, please?
Yeah.
You are setting this up in the bulk, but ultimately, will you be able to translate everything precisely into the boundary theory? These statements, the reason I'm saying is bulk, locality, etc., is approximate, right? So when we say, you're separated by so much in the bulk, one has to be a little careful about whether it's a diffeomorphically invariant statement, etc. So, I'm just curious.
Yeah.
Will you?
Right.
Yeah.
Right. Yeah. So the way to think about it is the following. So I would say this is an intrinsic boundary construction. So this, yeah, as I will make a little bit more clear later, that this we are in the leading order in one-way expansion.
Mm-hmm.
So in the leading order in one-way expansion corresponding to leading order in Newton expansion in the Bach, and in that regime, indeed all the points are sharp and the distance are sharp, and the distance are sharp, and then indeed we are the input is the Bach reconstruction for the right and L region. Okay. And so because we feel we understand the Bach reconstruction for the right region, for the region outside the horizon, and just using the standard ideas. If it is not, I won't say it's fully understood, but I would just say it's much better understood, and than the region inside the horizon. So we'll use the our understanding of the region outside the horizon as a starting point to see how the region inside the horizon emerges from the boundaries here. Okay. Yeah. So the input, everything outside the horizon, we believe can already be formulated in terms of intrinsic CFT language, and then what I'm describing here then can be considered as an intrinsic construction of the region inside the horizon. Okay, great. And just you said it just to make sure. What we'll do then is to think of the bulk as being mapped to the boundary using the HKLL kind of construction, right? You don't actually have to use HKLL here. Here you can use some kind of generalized. Yeah. So let me just clarify the language a little bit. You can say this. Yeah. So HKLL is normally say to express the Bach operator in terms of local boundary operators, and but there are subtleties to do that in the black hole geometry or in the ADS window, because we know that that kind of expression is divergent. And then actually the better way to think about it, which is just say the mode expansion in the Bach when you write it in terms of A and A dagger, and that A and A dagger are actually boundary operators. Okay, generalized free field construction, basically. Exactly, because that A and A dagger are boundary operators. Okay. So from that identification, the any Bach operator expressed through that mode expansion are just automatically boundary operators. Okay, got you. Okay, thank you. Good. So now it turns out, even though in general this
just a small clarification regarding this figure. Is there some significance why you draw the shaded triangle only upwards and not downwards?
Yeah, so this is for the this is just for the S greater than 0 evolution. Okay, so it does only smear to the future of this thing. Yeah, that's right. Yeah. Okay, so that's some detailed thing that you actually check, because a priori it's not clear if it just some non-local thing. It could be
to the past of that v equals constant line as well, right?
Yeah, that's a very good point. That's a very good point. So, so I believe this is the case. Actually, I'm not 100% certain. Yeah.
Okay.
Yeah, because the kernel is somewhat complicated. The kernel is somewhat yeah. So indeed, this picture should only be understood heuristically. Yeah. I think there might be a chance there's a spread down. Actually, I'm not certain. Yeah.
I was talking about the v less than the v naught region. So the lower edge of the triangle seems to be some v equals constant, right?
Sorry.
Just where you have the double arrow u1.
Yeah, maybe I'm not understanding your question. Yeah.
So along the line where you have drawn this double arrow u1.
Yeah.
So that edge, is that edge something that comes out of the formula, or?
No. This is completely heuristic. Don't take this.
I see.
Don't take this diagram seriously.
Okay, thanks.
Yeah, the whole point of this diagram is just to show that the spread is non-local.
Okay, thanks.
Yeah. Any geometry contained in this spread region, you should not trust it.
Okay.
It's not drawn according to any precise formula.
Yeah. Okay, thanks.
Yeah. Okay, good. So even though in general it's non-local, and this non-local pattern is actually rather complicated, we don't have a very precise way to describe them, this non-local pattern, other than this kind of sharp signature for the causal structure. But turns out when you take the large mass limit, if this operator have a very large dimension, and then this evolution actually becomes simpler. It becomes simpler. It turns out, in this case, if you also average over the boundary spatial direction, so that you only can concentrate on the time direction, so that you only concentrate on the Kruskal plane, and it turns out in this case this evolution becomes local. Okay, and so actually this evolution becomes local, and it transforms. So this is purely emergent from the boundary. So we didn't put any input of the Kruskal coordinates in doing this kind of construction. It just come out. You look at the complicated formula of this evolution, and then you find that this complicated formula can be written in a very simple way in terms of these Kruskal coordinates. And the way is that this phi translates into a new point xs corresponding to this transformation of the Kruskal coordinates. Okay, and so this is u0 plus s. U just translate by translation, but v translate in a more complicated way. And so this is a flow pattern. So if you just take a point and take the s greater than 0, flow like that, s smaller than 0, flow like that. Anyway, so this is a flow pattern starting from different points. And so one thing about this formula is that it actually preserves the boundary. So if a point lies on the boundary, actually remains on the boundary, okay, due to this consequence of this VS transformation. And so this is the formula for the constant S slice. So suppose we start with the t equal to 0 slice of the Schwarzschild geometry. So this is about a Schwarzschild geometry, and then add some positive S, and then you flow like that. Okay, and then you see that this indeed corresponding to another Cauchy slice, which actually crosses the horizon. Okay, so that's why we call this Kruskal-like evolution. This is not exactly, say, the Kruskal time, but it's a Kruskal-like evolution. Okay, so just to summarize the basic picture I wanted to convey to you is that if we use the standard ADS-CFT, say applied to the right and the left region, and we only know that somehow the physics in the right region is due to the CFTR at the finite temperature, and the physics in the left region is due to CFTL at the finite temperature. But it's not really clear they're connected, or they have this F and P region, etc. In particular, they're causally connected. Okay. So there's this ER equal to EPR kind of conjecture, which tells you they should be connected because they're entangled. But that normally refers to a constant time slice, say, but does not refers to the causal connection. Okay. So what this US does is really to make it into a complete causal picture. In the sense you start with this R and L, and then you see the emergence of this F and P, including the causal structure implied by the horizon. Okay. And this US, so in the sense that this US leads to a new emergent infalling time. Okay. In particular, I also want to emphasize there's infinite number of choices of such infalling times. So in principle, you can actually construct many, many of them. So what I described is just one particular example. Okay. And by constructing, this is diffeomorphism invariant. Okay, it does not refers to any bark coordinates, even though we can map it to the even though we can map to the Kruskal coordinate, but the construction itself does not use Kruskal coordinate as an input. Okay. Good. Any questions about the result I want to convey?
Yeah.
So I had a question.
Go ahead.
Yeah, can I just ask one question? So this construction, does it hold for non-perturbative conform field theories also, or in the larger? Maybe you said it and I missed.
So for non-perturbative?
Yeah, I mean for finite n.
Oh, no. So at the moment, I think this construction should work order by order in 1n.
Okay.
For finite n then the picture is not clear. Yeah, that's certainly a very important question. Yeah.
I see. Thank you.
Yeah. So
sorry, I had the same. Just let me, if you don't mind. Sorry, Hong. Just same sort of clarification that even for the large mass case where the transformation became local, is that the case, strictly speaking, only at infinite n? Or
infinite n. Yeah.
Okay. Thank you.
Yeah.
And just to follow up on that, are you using strong coupling anywhere, or is this just a generalized field construction?
Yeah, this in principle does not use strong coupling anywhere.
Okay, so in principle, I could do this construction in free field theory at large n.
So free field is tricky. I think you can use for weakly coupled series.
Okay, got it. Thank you.
Yeah.
Sure.
One more thing I want to emphasize, which actually I forgot to, 1 second. I wanted to say make a remark, but I forgot that remark. I think it will come back later. Oh, right. I want to say, when we go to finite but very large n, we expect this structure to be approximately present, okay? And but how it is approximately present in what form? That's not. That's still unknown. Yeah.
Thanks.
Okay.
Sir.
Yeah.
Yes, sir. If you have some black holes in the LR in the left or right region, will that affect the time slicing?
Because the if you have some structure in the left and the right region that will change the states, you will see later I will use the states in the essential way, and so that will certainly change the time slicing. But the construction works. The general idea works, but the specific time slicing will change. Yeah.
It's in the case of black holes, we'll have some quantum error correction due to the Hawking radiation. How will that play into the time slicing?
Sorry, say it again.
If we have some physical black holes in the left or right region, it will also have some Hawking radiation. So how will that have some quantum will that have some kind of quantum corrections to the time
So
slicing?
you're talking about to have some additional black hole in
Yes,
this in this internal black hole geometry?
No, sir. Outside.
Yeah. So you say have some additional black hole outside the internal black hole.
Yes, sir.
Yeah. It will change. The story will become more complicated. But I think that as you will see, the construction should still apply. But what kind of slicing will result? I don't know. Because we haven't looked at those situations. Yeah.
Okay, thank you, sir.
Yeah, but our procedure should still give you some kind of infalling time. Yeah. Good. Okay.
Sorry, Hong. So I had some question about the non-locality and the sharpness of this S, the critical value of S. So you have shown that there could be a fuzz. It's a little bit related to what Raghu was asking. You have said that there could be a fuzz which is like, maybe let me try to, okay. So you have shown that there could be a fuzz like this. Sorry, you didn't show that one. You showed this one. But my question is that suppose that there is a fuzz like this, the one that I'm drawing now, this one. Then S will be S will not be sharp, right? Because S is basically the distance along this along this light cone. So the kind of fuzz that you showed indeed does not affect this distance, but if there is a thing like this, this one, then it would affect the light cone distance to reach from this point, this guy to the other guy.
You mean if I start with the operator which is smeared?
Yeah, that's right. If the smearing is of the kind that I'm showing here, which affects the light cone distance.
It will. It will. Yeah.
So why not? Why isn't the fuzz of the kind that I drew?
Sorry. Maybe I don't fully understand your question. Yeah, if you smear this operator in the right region,
isn't there some automatic smearing in the bulk operator construction procedure itself?
So there's not really. You can always see you say you want to regularize that operator. Is that what you want to say?
Yeah, I'm saying that in terms of, in terms of a boundary construction, if I want to write down some operator at some particular point in the bulk, okay, then there would always be some amount of non-locality, not necessarily only the non-locality in the causal wedge kind of stuff that you were drawing, but also of the point itself, or not? Maybe I'm confused here.
Yeah, I don't think if you write down a bulk local operator itself, there's no non-locality. It's corresponding to a non-local operator on the boundary. But the bulk operator itself, if I just draw an operator like that, and that just is the local operator in the bulk.
Okay, that's the local operator. So now that will correspond to some non-local construction in the boundary then.
Yeah, that's right. Yeah, this is a non-local operator in the boundary.
And then I'm constructing this US and U minus S. Presumably, these are boundary field theory
that's right.
constructions.
That's right. Yeah.
So then the left-hand side, phi XS, will, so there is some kind of smear that represents phi RX. Smear in the boundary, and then I'm doing sort of this similarity transformation with respect to US, and so the result is something that is non-local in the boundary.
Yeah.
How am I so sure that when I apply the bulk boundary map to go back to the boundary to construct this phi xs, that is the point in the bulk.
Oh yeah, that's a non-trivial procedure. So you're asking this formula?
Yeah.
This is a non-trivial procedure, and if you look at our paper, it actually comes out in the rather miraculous way.
I see.
Indeed, it actually comes out in a highly non-trivial way. If you look at the formula, it doesn't look like something local. But turns out to be something local.
I see. So it doesn't. I mean, it's a bit of a surprise, is it?
This is definitely a surprise. This is you have such a simple formula emerges from this seemingly. If you look at the equations, they look rather complicated.
Right.
But somehow that kind of very complicated equation just can be organized very simply using this transformation.
I see.
Okay. So that's why I call this is emergent, because if you just look at this operator, it's actually rather complicated.
I see. Okay, thank you.
Yeah. Good. Okay, so now let me talk a little bit about the technique, the hint we used to do this construction. And so this we go back a little bit to entanglement, how we describe entanglement in relativistic QFT. In particular, this type 3 von Neumann algebra structure. So let's just consider how we normally describe entanglement of a quantum, say ordinary quantum system, say finite dimensional. Say we can take H1, say suppose your Hilbert space, suppose your system is separated into two parts, and your Hilbert space have tensor product structure associated with these two parts. And then we can define a reduced density matrix associated with one part by tracing over the other part, say, suppose psi some global states defined for the full Hilbert space. Okay. And then you can define rho 1, and rho 1 contains all the quantum information, say, regarding entanglement, etc., between 1 and 2. Okay. And of course, the goal of quantum information is to extract, this rho 1 in principle contains too much information. And we only, so the goal is to extract the information from this U1, rho 1 in the simple way. And for example, von Neumann entropy is one of the most important quantities, etc. Okay. But there's something interesting happens if you can also do similar thing for rho 2, okay, by tracing over 1. So turns out when the rho 1 and the rho 2 are both full rank, okay, so rho 1 have some rank, but if rho 1 and rho 2 are both full rank, that means they can be invertible, okay? Then in this case, then we can construct, then there's a new construction, there's a new structure. We can construct so-called modular operator by multiplying rho 2 times rho 1 inverse. Okay. So this modular operator have the following properties. When it acts, say if we exponentiate it with an imaginary exponent, and then if we act on the operator in the system 1, it remains in the system 1. And if we act on the operator in system 2, it still remains in system 2. Okay, so in the sense it is automorphism of the operator within for each subsystem. Okay, and so this structure is called the modular flow. Okay. So the existence of this modular flow can be considered as an indication, okay, that actually, So this is an indirect way. Say if a modular flow operator exists, then rho 1 and rho 2 must be full rank, okay. And when rho 1 and rho 2 are full rank, so this means 1 and 2 are highly entangled. Because if they're not entangled, then rho 1 will have rank 1. Then rho 1 will be pure state, will have rank 1. Okay. Similarly for rho 2. So modular flow can be another way to say these two systems are highly entangled. Okay.
And sorry, just quick clarification, Hong. This also requires the dimension of H1 and H2 to be equal. Is it full rank means presumably?
That's right. Yeah.
Okay, thanks.
Yeah, for the finite dimensional case, that requires them to be equal. That's right, exactly. Thank you. Good. So now let's consider in the QFT. So QFT. So let's consider QFT in the Minkowski space-time. And so we can separate them into, so consider the simplest case, we separate them into, say, 4 Windler regions. The right region, left region, just consider half space, and the causal diamond of the right half, which is the right region, and then the left region, etc. So it is often said that in the Minkowski vacuum state, the Minkowski vacuum state can be interpreted as a sum of your double states for the right and L Windler patches. Okay. So so this is a standard statement used in many places, which give us a lot of insight for many different questions. But strictly speaking, this statement is only correct in the discrete when the series has a cutoff. Okay. So more precisely, this series is only correct in the discretized series. So if you put the series on the lattice, okay, and the lattice for the right and the left are separated, and then this statement certainly is correct. Okay. But this statement is no longer, is strictly speaking, say mathematically speaking, this statement is not correct in the continuum limit. Okay. So in the continuum limit, actually there are some fundamental differences between this discrete and the continuous case. Okay. And so in the continuum limit, we can no longer actually think of this as a sum of your double state. So let me just to make this statement a little bit more precise, let me just compare the differences between the discrete and the continuum limit. Okay. So in the discrete case, when you put the system on the lattice, and then automatically there's a local Hilbert space for the H, for the L and the right region, and then you will have then you just have a tensor product structure between the H and the right and L region. But in the continuum limit, actually, there's no such a tensor product structure. Any states which are direct product between the state in the right Hilbert space and the left Hilbert space actually have infinite energy. Okay. So, and those states are not in the Hilbert space. And so in the continuum limit, actually, you cannot factorize your Hilbert space. And in here, you can just trivially define reduced density matrix because you have tensor product structure. But in here, you cannot. Okay. And here you have a finite entanglement entropy, which depend on your lattice spacing. But in the continuum limits, when you take the lattice spacing go to 0, the entropy is infinite. So there's not a well-defined entropy. But what's in common between the two is that the modular operator and the modular flow exist. So in the sense, in the continuum limit, the only structure left regarding the entanglement between the right and L region is the existence of the modular operator and the modular flows. Okay, and because everything else, all other structure don't exist. But actually, there's also fundamental difference between the modular operator in the discrete and continuum case. In the discrete case, the modular operator can be factorized, but in the continuum limit, you cannot. Okay, you cannot write continuum limit and the modular operator as say a product of some operator in the left region and some operator in the right region. You cannot write that way. And also in the discrete case, there's no sharp light cone. Okay, whenever you have a lattice, so there's always some small tail which can leak outside the light cone. But of course, in the continuum case, this sharp light cone. So it turns out all these differences.
Can I ask a question?
Yeah.
How do you even define modular operator and modular flow in the continuum case if you don't have a reduced density matrix, something like ρ2, ρ1 inverse, etc.? How do you define them?
Right. Yeah. So this is guaranteed by this called the Tomita Takasaki theory, which they show once this vacuum state satisfies certain property, and then such modular flow exists. Yeah.
I see.
Yeah. So in the Rindler case, you can actually construct modular operator and modular flow explicitly. That just corresponding to the boost operator. Yeah.
Okay. Thank you.
Right. So in the sense, in the continuum case, this is the only way we can talk about the entanglement between L and R. Okay. So it turns out all these differences between the discrete and the continuum case can be traced into one fundamental fact, okay, regarding the difference in the operator algebra between in the right region. Okay, so it turns out if you look at the operator algebras in the right region, okay, and for the discrete case and for the continuum case, and they have different structure, and all these differences, which is not obvious, okay, all these differences can be attributed to the difference in the operator algebra structure. Okay, so in the sense that the difference in the operator structure gives the fundamental reason between all these differences. Okay, and so the difference is that in the discrete case, the operator algebra is actually a type 1 monomer algebra, and for the continuum case, it's a type 3 monomer algebra. So we're not going into details, say, of definition of von Neumann algebra or how to classify them, etc. Just heuristic speaking, you can view these properties of this right column as some kind of hallmark, okay, of this type 3 von Neumann algebra. Okay. Yeah, and yeah.
Can I ask a question?
Yes.
Is the statement about factorizing, is the statement that you can factorize the Hilbert space only in the discrete limit? Is this true about gauge theories as well, or is it special to just gravity?
Oh, so here we are just talking about some boundary theory. So from boundary theory, say we can just, yeah, here we just consider some very simple quantum field theory in Rindler space. For example, they just consider scalar field theory, and then this statement is true. Indeed, if you consider gauge theory, then the story is more subtle. Yeah, but to illustrate this point, the fundamental differences, just a simple scalar field theory would be enough.
No, so actually my question is more basic than this, that even if we are not working with a holographic theory, if we have just a gauge theory, and if I want to consider entanglement entropy between two regions in a gauge theory, can we make sense of Hilbert space factorizing in region A and region B because of Gauss law, or can we, because of Gauss law, can we not?
Yeah. So if you consider gauge theory, of course, there's more subtleties because of the gauge freedoms, etc. And so there's new so even in the discrete case, if you put the gauge theory on the lattice, even in the discrete case, there are subtleties which you cannot really factorize your Hilbert space, etc. Yeah, but that kind of complication is not essential for what I'm going to talk about here. Here I'm just talking about consider the simplest theory, and so these are the fundamental differences. I'm just use this to introduce the operators algebra structure. Yeah.
Thank you.
Sorry, Hung, can I ask one question?
Yeah.
So again, just for the simplest theory, say scalar theory, as you emphasized in the continuum limit, you cannot factorize the Hilbert space, etc. But there is a well-defined notion of local operators, right? I think, which lie either in the left or the right, right?
Right.
Right.
Yeah.
And my question to you was, is there a sense in which the complete set of all operators can be built out of a basis consisting of left or right localized operators and their tensor product, or is that not true?
Yeah, that's a very interesting question. So for the standard quantum field theory, you can, okay, because for the standard quantum field theory, for the standard quantum field theory, because this L and the right, they already give you a single Cauchy slice. They cover a full Cauchy slice. So in principle, you can express all future operators in terms of the operator on this Cauchy slice. Okay. And but for generalized free field, this is not obvious, because for generalized free field, it's not, you cannot evolve from a single Cauchy slice. And but actually, it turns out for the generalized free field, this property is still true. And actually, we showed in our paper, just some byproduct of our results. You can show even for generalized free fields, if you know the operator algebra for the right and the L, you can actually reconstruct F and P. Yeah, even for generalized free field, which is naively not true. Yeah, which is naively not more non-trivial question. Yeah.
I see. Okay. Thank you.
Yeah. Good. So the story is actually general for relativistic quantum field series. So for any local region, so I want to emphasize any local region, okay? So because this distinction is going to be important later. Local operator algebra can be associated with type 3-1 modular algebra. Okay, so the local operator algebra in the local region can be associated with some type 3-1 modular algebra. And so this is a fundamental fact about the relativistic QFTs. Okay. And then entanglement for any local region then can be, say, with its complements, can be understood in terms of modular flows and associated with such a algebraic structure.
This local region does not have to be an open set, right? I mean, in the sense that you cannot split the left and right both in terms of open sets.
That's right. Yeah. You have to have an open set. That's right. Yeah.
Okay.
Yeah. By only any local region, I do mean some kind of open set. Yeah. Mm-hmm.
So it's like you leave out the boundary point in the middle.
Yeah, the boundary point is always tricky. Yeah, the boundary point is always tricky. There's a common point. Yeah.
I see.
Mm-hmm. So now let me talk about the structure, some additional structure which comes with this type 3-1 von Neumann algebra. Okay, and this additional structure will be crucial, okay, for our purpose. And so here I will use a little bit mathematical language. So let's say M is a von Neumann algebra, and some vector omega is cyclic and separating for M. Okay, so now let me translate this into more mundane English. So by M, say, let's just imagine M is the operator algebra in the Windler right region. And then this vector, say, you can consider as a Minkowski vacuum state. Okay. Saying that this Minkowski vacuum state is cyclic and separating for this operator algebra. So this is essentially the operator algebra way to say, if you could define a reduced density matrix, and then the reduced density matrix for this region and for this complement, they are both full rank. Okay. But of course, as we said, for quantum field theory, you cannot talk about reduced density matrix. And of course, even if you can talk about reduced density matrix, the reduced density matrix will be infinite dimensional. But this cyclic and separating is the generalization of such kind of full rank statement to the quantum field theory case. Okay. Yeah, we will not explain what this cyclic and separating really means. The physics is just like that. Okay, now let's suppose there exists another von Neumann algebra, which is a sub-algebra of M. Okay, with the following property that this omega is cyclic for N. Yeah, now I have to explain what cyclic means. Cyclic means that if you act the operator, all the operators N on omega, the resulting space is, the resulting states are dense in your full Hilbert space. Okay, so this is called cyclic. Okay. And then say suppose this is cyclic, and then and also suppose the modular flow of M acting on N. So N is the sub-algebra of M, so you can act modular flow of M on it. And suppose if I take modular flow with one side, with t smaller than 0, suppose this take you, suppose this still take you inside N. Okay, so this property means if I do modular flow for t smaller than 0, so it does not take you outside N. Okay. Suppose there exists such N, okay, which satisfy these two properties. Then you can show, okay, then you can show that for type 3-1 algebra, there exists a unitary group with the following properties. So this is a powerful theorem from Borchers and Westbrook in 90s, that there exists a unitary group which generated by some Hermitian operator, and this Hermitian operator is bounded from below. Okay. So again, I said this bounded from below give you some kind of Hamiltonian. Okay, because if you say what distinguish time translation and spatial translation, or some other internal symmetry. So what distinguishes the time translation and other symmetries is because time translation is generated by an operator which is bounded from below. A spatial translation is not. Okay, any internal symmetry group is not. Okay, so that's why. So that means when you can find such a sub-algebra N, okay, of your von Neumann algebra, and then there is an emergent Hamiltonian, and then there's an emergent time S, okay, associated with this Hamiltonian. And so in particular, this actually annihilates your vacuum state. Yeah, this leaves your vacuum state invariant. Okay, so this can be used to generate new times. Okay, so that means if you have this structure, then your theory actually have some emergent new time, which is not encoded in your original Hamiltonian. Okay, and this is purely arise out of the operator algebra itself. Okay, guaranteed by your operator algebra. Such kind of time, new times are guaranteed by your algebraic product, by your algebraic structure. Okay.
Just a quick clarification, Hong. Is this theorem false for type 2 and type 1 algebras?
Yeah. I think this theorem does not exist. Yeah. There's a paper by Borchers. He showed that this structure only exists for type 3-1. Yeah.
Got it. Okay. Thank you.
Okay. Now let me give you a very simple example of such kind of emergent time.
So, sorry, Hong, please excuse me. Just to make sure. So the chain of argumentation is that.
One more clarification.
Oh, go ahead, Siddharth. Go ahead.
Sorry.
I think there's another question. I'm just waiting. Sorry.
Oh. But
okay. No. Maybe not. I'm not sure. Okay, let me
I just wanted to ask, in this construction, is G is not unique? Is that's what you're saying, right?
Sorry, say it again. Sorry, I didn't hear the question clearly.
Sorry.
Siddharth, maybe you can type the question. We can't hear you.
Can you hear me?
Yeah, now we can hear.
Yes. Go ahead.
Maybe there's a connection issue at Siddharth. And Sandeep, maybe you can ask the question.
Hello?
I just wanted to get a quick, so I understand the flow of logic. So the what you are saying is, if you take some simple theory, let's say like a scalar.
Yeah, I just wanted to, in this construction, is G unique?
Oh, yeah, G is unique. If you give me n, then the G is unique. But for each choice of n, you have a different G. So given me n which satisfies this structure, then the corresponding G is unique. But in principle, you can find, if you can find many different n, then you can have different possible G. Yeah. Sorry, Sandeep, you have other questions?
No, just a quick clarification. So the chain of logic is that if you take a simple field theory, say in the bulk, like a scalar field theory, then it will correspond to a type 3-1 algebra. Is that correct? Yeah. And then you will use these theorems. And again, just to make sure, in the kind of free field like limit, whether it's gravitons or whether it's a scalar theory, won't make much of a difference, or what do you think? Just to ask you.
Yeah, I think it should not make much difference. Okay. But for the graviton case, of course, there again will be subtleties associated with the gauge.
Correct. Yes.
The gauge symmetries.
Yes.
So, but I suspect if everything is sorted out, I think it should still have the same structure. It just it's just technically more complicated. Yeah.
Okay. Thank you.
Yeah. But that's just my expectation because I'm really not that familiar with all the intricate subtleties with the graviton case. Yeah.
Sorry.
Just which I think you know better than me. Yeah.
Just a curiosity. So these mathematicians, do you know what their motivation was? Were they also looking for some Hamiltonian-like operator? Was that the back of their mind?
Oh, I don't think they were looking for such things. They certainly didn't use the language of emergent time.
Mm-hmm.
They you will see why they come up with this structure. The structure is very natural when you consider this Windler case. We'll explain this from the Windler case. You will see why.
Okay, thank you.
Let me just give you an example, then you will see. Okay, so the key thing is that you need to have a type 3-1 monomer algebra M, and then you need to have a sub-algebra which satisfies this kind of properties. Okay, so this is called half-sided inclusion. Okay, so if you translate by one sign, does not take you out. So now let me just give you a simple example. I think that is also an example which motivated the Westbrook and the Borchers to prove such kind of powerful theorem. So there's a trivial case for this theorem. Is that let's just look at the Windler region. Let's look at the M to be the operator algebra in the right Windler region. Okay, so as we said, this should be a 3-1 monomer algebra. And now let's look at the sub-algebra associated with another Windler region, but it just narrowly shifted in the x minus direction this way. Okay, so this, and obviously this N is the sub-algebra of M. Okay, and then you can show also this half-sided modular inclusion is automatically satisfied because the modular operator for M is just the boost. So under boost for one sign, you just take N to itself. Okay, just when you boost in one direction, the N just goes to itself, and so this condition is satisfied. Okay, so that means in this case there is an emergent G, which is bounded from below. And in this case, it turns out this emergent G, of course, you may have guessed, is actually precisely the translation along the x minus direction. Okay, so in this case, the G just corresponding to the translation in the x minus direction. And similarly, you can do you can just check. Yeah, so now this G then can be used to, once you have this G, you have S, then you can also act on the original M. Okay, and for S smaller than 0, this is just null translation. So for S smaller than 0, just translate again M to itself. And in particular, for some particular value, it takes the M to N. Okay. But when S greater than 0, then this null translation will take M into this F region of the windowless spacetime. Okay. So just by using this kind of construction, okay, essentially, if I only give you the operator algebra in the right and the left windowless region, and then you can actually construct the full Minkowski spacetime. Okay, so you can construct the F and the P regions from the algebra of the right and the L regions. Okay, of course, in this case, it's more like a triviality because we know this can be done. But the power of the theorem is that this just works for very general situations. You only need to find this true von Neumann algebra, and then this emergent time will appear.
Sorry,
So
I didn't understand the argument how this S flow will take you outside M.
Yeah.
How would the S flow take you necessarily outside M?
Yeah, because this is just translation along the x minus direction.
Okay.
So if you take this to be M, and if you translate into x minus direction, then we'll just take you to another bigger Rindler wedge. Yeah. Yeah.
But in general,
the other side just take you to a smaller Rindler wedge.
In general, is there any statement in the theorem which says something to this effect that if you evolve, then you somehow go outside or something like that?
No, their focus was really on the, if you look at their theorems, it's really look at this one-sided structure.
Mm-hmm.
So they can show that when you have this thing, and then you will always take you inside M. But then of course, if you take the other sign, then can take you outside M. But then here they cannot make general statements. So their theorem does not involve that part. And so we have to generalize that part. And that is in the case of generalized free field, you can actually generalize them. Yeah.
Thanks.
Hong, this G is the same as P plus, is it? I mean, is the moment?
Yeah, exactly. It just P plus, yeah.
So then how come it is bounded below?
It is, because G plus is just H plus P. So H plus P is bounded from below because H is greater than P.
P plus because it's the light confirmation. I see.
Right, yeah.
Thank you.
Good. So in the sense, in this trivial case, if you start with the Rindler time in L and R, okay, because if you have a Rindler region, you only have the Rindler time, and then we can actually obtain the Minkowski time. So this is essentially the inspiration we will use to generate the Kruskal-like time from the Schwarzschild time. Okay, from the Schwarzschild time. Yeah. So I'm way out of time now. Should I continue, or what's what's your rule here?
So how much longer do you need, Hong? We generally continue for longer than 1 hour.
Yeah, maybe 10 minutes I can try.
Sure, no issues, you can take it.
No. Can I make a request, Hong? If it's okay with you, many of us will be happy to stay for half an hour more. It's a beautiful, clear presentation for someone like me. Please don't hurry too much, if Pushkal will allow it. Pushkal.
Okay.
Sure, up to Hong.
Okay.
Yes.
Okay, thanks. Yeah. So I will just keep going. Yeah. Mm-hmm. Okay, so now the key is that if you have a type 3Y monomer algebra, and then you appropriately choose some sub-algebras, then that can lead to new emergent types. Okay. So now let's see how this works for the black hole case. Okay. So now first let's go back to the black hole story. We say the internal black hole is described by the tensor product of CFT-R times CFT-L in the thermal field double state. So here, just for simplicity, let's just consider the CFT lives on sphere. Okay, just the standard story on the sphere. Okay, and then the full operator algebra of the CFT-R or CFT-L is type 1. Okay, this is just by definition. Okay, and so this should be distinguished from what I said earlier, the operator algebra in the local region. Okay, the operator algebra in some local region is type 3. But if you look at the full operator algebra, it's actually type 1, okay, because there is an obvious Hilbert space structure. But we
sorry, please excuse me, Hong. This is in the large N limit, because we just have a sort of generalized free fields rather they're analog in the field theory. Is that why it's type 1?
Yeah. So here the general state. Here I'm just making the general statement at finite n.
At finite n, I see.
Yeah, at finite n, the operator algebra is just type 1. Yeah,
I see. So just the fact that it's on a sphere, I mean, it's still a field theory, right? But it's
a field theory. Yeah,
I see. Okay.
Yeah.
Okay.
So on the sphere, say if you look at the full operator algebra, it's type 1. But if you look at some sub-region on the sphere, it's still type 3. Type 3-1. Yeah.
Thank you.
Okay. Okay, good. But now I want to argue in the infinite n limit, okay, or in the 1 over n expansion. So we always think about, say the way to think about this, we always think of large and finite n, but we do 1 over n expansion. Okay. So I want to argue in 1 over n expansion, then there is an emergent type 3Y monomer algebra. Okay, in the large n limit. So, and this emergent type 3Y monomer algebra then can lead to this emergence infalling time and the sharp horizon and the interior. Okay. So the object we are going to look at is the algebra generated by single trace operator. Okay. So this algebra can only be precisely defined in 1 over n expansion. Okay, because the when we take the n to be very large, and then we just take the algebra, any finite product, okay, any arbitrary product, say of single trace operators and sums, and the number of product, of course, should not depend on n. Okay. Okay, good. So let's consider such an algebra. And then, so if we look at, say, finite but large n, okay, and in the 1 over n expansion, and then so this AR is actually not the monomer algebra because it does not contain many operators. It only contains those finitely generated operators from single trace operators. Okay, so I will not go into the technical detail here. So acting on the full Hilbert space of the CFT-R, this is actually not the monomer algebra. But in the large n limit, actually there's another Hilbert space. So this is a Hilbert space of small excitations around the thermal field double state. So by small excitations, that just means you act finite number of operators of single trace operators on the thermal field double state. Okay. By finite number, again, just that number should not depend on n. Okay, that number can be arbitrarily large, but cannot depend on n. Okay. So you can show that the state obtained this way by acting this product of single trace operator in the thermal field double state that space have a Hilbert space structure. Okay, you can actually do it rigorously mathematically. So this is called the GNS construction. So that's why we call this GNS Hilbert space. Okay, yeah, but physically it's very easy to understand. This is just the space of small excitations.
So just
and now,
sorry,
yeah.
So I understand physically, in the bulk, it's just arbitrary number of gravitons, as long as that number doesn't scale with G Newton, and anyway, we are taking G Newton to go to 0.
Right, exactly.
Okay.
Yeah, that's the exact, yeah, as I will say in the next slide, that's exactly just the Fock space in the gravity side.
Okay. Thank you.
So now we can look at the action of this single orbit algebra on this Hilbert space. Okay, so I will describe the representation of this algebra in this Hilbert space to be MR. Okay, so to distinguish from the original operators. Okay, and so the action of this operator in this GNS Hilbert space, I denote the algebra as MR. So this distinction is important. Okay.
Sorry, yes. Doesn't this go towards answering a previous question about whether there could be a black hole in the outside region?
Yeah.
Because now constraint is that it should just be a graviton gas, and you don't want to have a very large energies, I would imagine, like as large as black holes.
So if you have a black hole outside, then you just don't start with the thermal field double state. Then you start with the thermal field double state with this black hole. You start with this more complicated state.
I see. Okay.
And then again, you have a GNS Hilbert space based on that state.
So that means this constraint can be bypassed always in that kind of way.
Yeah.
Okay.
Yeah. You just start whatever Bach states is fine. Yeah.
Okay. Thank you.
Okay. So now let's look at this algebra, which is the action of this on this Hilbert space. So now the claim, you can also similarly define a ML. So now the claim is that this algebra is actually type 3-1 Neumann algebra. Okay. So I will not go into detail how to, so there's various support of it. I will not go into detail of that. So there's almost, you can argue it from the point of view of thermal spectral function of single trace operators. You can argue from the point of view of say existence of the half-sided modular inclusion and translation structure. So a simple way to argue is just duality with the Bach. Okay. So let me just say a few words about this one. So in the Bach, we have similar object. We have the Fock space. In the Bach, we consider G Newton perturbatively in G Newton. Then you can construct then you can quantize your gravity fields around the Hartle-Hawking vacuum, and then you can construct the Fock space based on this Hartle-Hawking vacuum. And then you can have operate algebras of gravity field in the right region and the gravity fields, say, in the left region, which I call M tilde R and M tilde L. And then the standard duality between physics outside the horizon and the CFT then can be interpreted, can be described using this algebraic language as the identification of this GNS Hilbert space with the Bach-Fock space, and the identification of the vacuum of this GNS Hilbert space with the Hartle-Hawking vacuum, and the identification of the operator algebras. Okay, so essentially you just identify this single trace operator algebra acting on the GNS Hilbert space with the Bach field operator algebra acting on this Fock space. Okay, similarly with the left. And again, this is what we said the input of our construction. So this is the standard dictionary for the physics outside the horizon. Okay. And then because on the gravity side, M tilde R and M tilde L, they're just some sub-region for the Bach geometry. The Bach is a quantum field theory in the black hole geometry. And then they should be type 3-1 volume algebra. Okay. And so that's just the say be compatible with duality, and then they should be, then MR and ML should be 3-1 volume algebra. So now our goal is to find the sub-algebra. Now we have identified some non-trivial type 1 volume algebra. And then now the goal is to find some appropriate sub-algebra, okay? And then that we can find the US, okay? Mm-hmm. So to find the sub-algebra, let me make a general remark. So where the theorems of these half-sided modular translations ensure the existence of this US, finding it explicitly in general is very difficult. Okay, so in the simple case of Rindler, you can do it, but in general, it's very difficult. So, but in the large N limit, the algebra of single trace operators in JS Hilbert space actually can be described by a generalized free field. Mm-hmm. Okay. So in this case, we can actually significantly generalize this structure, this half-sided modular structure. So in this case, we can actually work out the expression of US. We can, just based on various constraints from this half-sided modular structure, we can significantly constrain the form of this US when it acts on the generalized free field. Mm-hmm. And you can show that this expression of US has a universal form up to a phase factor. Okay, so this is a highly non-trivial construction, which I will not show here. Okay, and so you can actually determine this expression in general up to a phase factor, and this phase factor will depend on specific algebras. Okay, and will depend on specific algebras. Okay, so the non-trivial thing is we have to identify some sub-algebra. And then for that sub-algebra, we have to find this phase factor. And then we are done. Okay. So here is a general remark. So let's consider a causal diamond and the two Cauchy slides associated with the causal diamond. So for quantum field theory, for ordinary quantum field theory, then the algebra associated with this Cauchy slides A1 and algebra associated with this the other Cauchy slides, they're equivalent. Okay, because they are just related by standard Heisenberg evolution. But this is not so for the algebra of single trace operators. They're actually inequivalent. So the reason is very simple, because what you should remember is the standard Hamiltonian for large N gauge theory, for large N theory, there's a prefactor N times a trace, okay? So if you use that Hamiltonian to evolve this algebra of A1, that takes you outside the single trace operator algebra. So that means actually algebra of single trace operators A1 and A2 are inequivalent. So this is also easy to understand from the generalized free field language. When you have a generalized free field, there's no equation motion. Since there's no equation motion, then A1, A2, they're just inequivalent. Okay, they're not related by some equation motion. And so this is very important. Okay, so this means in the large N limits, there's actually much richer algebraic, much richer set of algebras we can choose than at finite N. At finite N, they will be just equivalent. Okay. And so now we can construct emergent boundary times by choosing some sub-algebras. So now let's just imagine the boundary CFT is 1 + 1 dimension. Okay, so let's imagine the vertical direction is time. So this is boundary space time. The vertical direction is time, and the horizontal direction is a circle, which is this line is identified with that line. So the whole thing is like a cylinder. Okay. So we just said the full operator algebra, single trace operator algebra on the boundary is a type 3-1 in the large N limit. So that's the full operator algebra in the boundary. And now let's choose the sub-algebra to be all the single trace operator algebra below some time. Okay, so here let's say below t equal to 0. So if you look at the ordinary quantum field theory or quantum field theory or the boundary theory at finite N, then these two algebra are equivalent because both are equivalent to the operator algebra on the single Cauchy slice. Okay, because you can just do a Heisenberg evolution. But in the large N limits, these are just completely different algebras. Okay, they are inequivalent.
So, sorry, Hong, can you just, so this is a picture on the boundary, is that right? Okay, and just describe again. So you take the algebra of single trace operators just below some slice, t equal to 0, and just above, or anywhere below, just once again.
Right, so I have two algebra. I have M and N, right? So M would be the algebra on the full space-time, single trace operator algebra on the full space-time.
Okay.
And N is only the region below t equal to 0.
Okay.
So yeah, so at the finite N, these two are equivalent, but at the infinite N, they are not.
I see.
Yeah, because at finite N, they can all be equated to a single Cauchy slice, and then they're just equivalent, trivially equivalent.
I see. But at finite N, just the single trace operators don't form, do they form even an algebra? Okay.
Yeah, you cannot really define it. Yeah, I just say, no, I should say, sorry, I just misspoke. I should say at the finite N, the full operator algebra associated with these two regions, they're just equivalent.
Yeah. Okay.
But at the infinite N, we can talk about single trace operator algebra, and now they're inequivalent.
Yeah. Okay.
Sorry, Hong, I'm a bit confused about this point. How are they inequivalent for large and single trace sector?
Yeah, it's just the same reason. Just here, it just now the single now the different Cauchy slice is no longer equivalent. Yeah.
No, sorry. Even here, I was confused. So why doesn't Hamiltonian evolution relate them?
So what you should keep in mind is that the Hamiltonian, the standard boundary Hamiltonian, is equal to n times a trace. Okay. So the Hamiltonian is a single trace operator multiplied by a factor of n.
Okay.
And that n makes you when you exponentiate this operator, because that factor of n will take you outside the algebra.
I see. Okay. Thanks.
Yeah. Good. Okay. So similarly, you can choose n to be all the operator above t equal to 0. Okay. And you can also choose n to be not homogeneous in the spatial direction, again below some time. You can choose n not to be homogeneous but above some time, above some arbitrary Cauchy slice on the boundary. So for all these different choice of n, so in principle you have infinite number of emergent times. For all these different choice of n, you can show that this half-sided inclusion structure, they are satisfied. And so in principle, the infinite number of emergent times. Okay.
Sorry, Hong, a quick clarification question. Is the stress tensor included in the n going to infinity limit?
So depending on how you normalize the stress tensor. So normally the stress tensor is normalized if you just do the standard stress tensor by taking derivative of the metric. So that stress tensor again have a prefactor n before the trace. And that operator is not part of the algebra.
Okay.
But if you divide that operator by n, and then you only have the trace, and that is in the algebra. Yeah.
Okay, got it. Thank you so much.
So this n factor is crucial. You need that factor n to generate the finite time translation.
Right. That's exactly.
Yeah. Without that factor of n, because the standard OPE structure of single trace operator, you will only generate the 1 over n kind of time translation, so that will not generate a finite time translation.
Right. Thank you.
Yeah. Okay, good. So now we just have to find the u corresponding to this kind of n. Okay. So now but this is actually a non-trivial question. So finding n us is now a strongly coupled problem. Okay, because but as we said, in the generalized free field level, we can reduce it to a single phase factor. So now we just have to find that phase factor. Okay. So it turns out the phase factor can be found out by using a trick by going to the bulk. Okay. So we have a proposal, okay? So we propose that the operator algebra for this region N is actually dual to the operator algebra in the Bach region in this N tilde region. Essentially just draw the causal wedge of this N in the boundary series to the Bach, and then you have this causal wedge in the outside horizon. And this N tilde, so our proposal is that the operator algebra for N is actually dual to the operator algebra in this region N tilde. Okay. So now with this, so this identification, there's various self-consistency checks, etc., which I will not describe here. We discuss them in detail in the paper. Anyway, so here is a proposal, but with this proposal, and then we can actually use the duality to calculate this phase factor using the gravity. Because the gravity side, you have a generating field theory. Because even though in the boundary you have a generalized free field, but still the 2-point function is a strongly coupled 2-point function. We don't know how to calculate that intrinsically. So anyway, you can just use this construction to calculate this phase factor. It turns out this phase factor is precisely the familiar phase factor for fields for phase shift at the horizon. Okay, so for those people who are familiar with the, say, the mode expansion, say let's consider scalar fields, say mode expansion in the black hole geometry. So if you impose the scalar field to be normalizable at infinity, then scalar field at near the horizon is just two plane wave, superposition of two plane wave. It's an ingoing wave and an outgoing wave. The outside horizon or ingoing to the horizon, a two plane wave. And if you impose normalizable condition at infinity, and then that fixes a phase shift between the ingoing wave and outgoing wave. Okay. And precisely that phase shift, which goes into the phase shift for this US. Okay. And that phase shift, actually for myself, I've looked at that phase shift for 20 years. Okay. Very early on, from one of my early days of looking at the CFT, I look at that phase shift, I'm wondering what does that correspond to in the boundary theory? Because if you look at the correlation functions or etc., that phase shift just don't show up. And finally we see where does that phase shift show up? It actually show up in this US. Okay, show up in this US, and now you can just construct this US explicitly. And now for example, in this large mass limit, then you can just construct this flow pattern, and which I described earlier. Okay, and you can also, so by choosing N like this, what you generate is what we call the U kind of Kruskal flow, near the horizon corresponding to a U null translation. But if you do this kind of N, say above some time, and then you can show that actually corresponding to V time kind of a flow. So near the horizon, it's actually translation along this V Kruskal direction. You can also compose them. Okay, you can compose them. You can construct. If you compose them, you can, in principle, construct the full Kruskal flow. Okay. Yeah. Anyway.
One question.
Yeah.
So this G operator, which is where U is e to the I G.
Yeah.
S. So that G operator, does the theorem say anything about that being part of that operator algebra? Does it need to be part of the operator algebra in question?
No, that's not part of the operator algebra.
I see. Okay.
Yeah. So the G, just like the modular flow. So the modular flow operator is not part of the algebra. So it's an automorphism, but it's an external automorphism. Yeah.
Okay. No, I mean, I was wondering if the factor of N there in G would spoil because you want finite translations, right?
Right. So even G is not part of the operator algebra, but it's something you can construct. It's just like, even though the modular operator are not part of your single trace operator, but it's something you can construct explicitly.
Okay. Okay.
Yeah. Yeah.
And
Yeah,
just
let me
to
say this
clarify,
way.
so yeah, go on, please.
Yeah. So the modular operator, so the situation is similar to the modular operator. So the modular operator is some complicated combination of the left and the right algebra. You cannot write them in a simple way in terms of left and right algebra. Yeah. Similarly for this G.
Right. No, but I mean, even if it is combination, it could be just restricted to the single trace sector. That is also not the case.
That I think it is the
because I ask, because if it were, I would think that it would translate infinitesimally.
That's right. Yeah.
So that is also not the case, right?
Right. Yeah.
Thanks.
Yeah, that's right.
So just another clarification question. So can I think of this G operator in the present case as the integral of the bulk stress tensor on the let's say V horizon?
Yeah, indeed. So near the horizon. So heuristically, you can think of that the G operator will related to some kind of stress tensor integrated over the near the horizon. This is like a null shift, and so near horizon, this operator does have some very simple interpretation, just as yeah.
I see. Thank you so much.
Hong, can I ask you another very simple question? So just, okay, basically, are you saying that you can construct not the operator H plus P, as you were saying, but the e to the I or minus I H plus PS for any S in the boundary theory?
That's right, exactly. Because construct G is complicated, but we can construct the flow. Yeah.
I see. And so that's what allows you to then go inside.
That's right. Yeah. It turns out construct G is complicated, but construct this US is actually turned out to be much easier.
Okay.
And so that's what we did. We say you can reduce US to a single phase factor, then we can just find that phase factor.
Okay.
Okay. Yeah. Good. So maybe I should just stop here because I think it's late, and I can just answer whatever. Because for the rest it's more like some general remarks.
Okay. So let's thank Hong for a very nice and clear talk. If there are further questions, please go ahead and ask.
I have one question, but let me wait.
So one quick question maybe I can ask. So, here from the operator algebra point of view, the motivation to consider single trace sector was basically to get to this type 3-1 algebra, right? Which is crucial for this theorem to work.
Right.
But you also mentioned that if you look at an algebra supported in a subregion of a finite n CFT, that also is of type 3-1. Is that correct?
Yeah.
So then could one try to use a subregion algebra to perform such a construction and get something interesting?
Yeah. So you see the reason to restrict to this single trace operator algebra is actually not. The purpose is not to really to get this type 3-1. Just type 3-1 somehow just naturally follows from it. So the purpose is that if you want to understand the Bach geometry,
right?
If you want to understand the Bach gravity, say perturbatively in G Newton, then you have to look at single trace operator algebra because all the Bach fields and because the geometry is the geometry felt by this Bach field. And all these things are related to single trace operators.
Yeah, I agree. But just in case if a theorem is giving some sort of a Hamiltonian even in some finite n case, then one could ask question as to what does this mean?
Yeah, that's right. You see, if you look at that type 3-1 operator algebra for the full operator algebra in some local region,
okay,
then indeed there's a type 3-1 there. There might be some but you see, in that case, to find the subalgebra is much more difficult.
Ah, okay. Yes. Okay, fine. Yeah.
Yeah. You see, here, the existence of the subalgebra also is very much due to the Nagian.
I see. Okay. Thank you.
Yeah. Actually, I have a comment here. Actually, that's my my general comment here regarding the generalization. Yeah, actually, I was going to talk about if you look at the sub-region in the boundary theory. So you can consider the boundary CFT. So let's just, for simplicity, consider the vacuum states and just some sub-region R. And indeed, then there's a full operator algebra which is type 3-1. But actually, even in this case, there's an emergent type 3-1 associated with the single trace operator algebra in this region. So actually, even if you consider the vacuum state, consider some sub-region, there's some kind of new emergent type 3-1. Okay, and this new types, emergent type 3-1 will have the implications for the Bach physics, etc. Yeah.
I see. Thank you.
Yeah. Can I ask a question?
Yeah.
Okay. No, Hong, thanks a lot for a very, very nice and very helpful talk. Let me just try to understand in a sort of simple way what you've done. So, suppose I take the boundary theory in the large N limit, I look at single trace operators, they behave like free fields. The OP is suppressed in 1/n, etc. Then I simply manufacture bulk fields out of that by, putting in the bulk Bessel functions, etc. In the generalized free field construction. Now, suppose I were to say, okay, if you want to have a bulk operator which is in the forward region, I know how to propagate the solutions in the left and right regions into the bulk for a free field in the bulk. So I will manufacture for you a field, an operator in the boundary, which is now sensitive to the forward region. Suppose. Right. Now, you've obviously done more than that, but what exactly, what has been done, just so I understand?
Good. So the aspect you described is already well known.
Yeah.
So many people have looked at that, but that construction, you have to use the Bach Kruskal time or the Bach horizon structure as input, okay, to do that construction. Our goal is not to get that formula. That formula you can get by the procedure you described, and that was described by other people, by HKL and Raju Papadodimus. But our goal is not to get that formula. That formula was known. Our goal is to understand the emergent time. Because that construction assumes already as input the Kruskal time. But we want to see where this Kruskal time emerges from the boundary sequence.
So this operator U of S, in effect, by generating translations along U, you say is that. I see. Okay. I've got one more, but let me wait in case somebody else is. No one else.
Hong,
Please.
Could you make some remarks about whether you see any signatures of the singularity in your modular flow, in your S flow?
Right. So yeah, that's a very good question. We expect you should be able to see, but we haven't found very sharp signature. We have not found a very sharp signature, and we actually tried very hard. Tried 6 months, but the you see, the problem is that in the large mass limit, going to the singularity is tricky, because in the large mass limit, the limit when you take the mass to be very large, and the limit going to the singularity, these two limits don't commute. So that makes that calculation rather tricky. But now if you go to the finite mass, and then you get a highly non-local transformation involving all kinds of hypergeometric functions. And then to study the analytic structure of those hypergeometric functions are rather intricate. So yeah, so we don't have a full picture. Yeah, but I expect it should be there. Yeah.
I see. Okay, thank you.
So just along those lines, I know we had this discussion last time as well, so pardon me, but there is this question about the commutant of your region N. So if you could go back to the slide that has the picture of N in the bulk, okay. N tilde.
Okay.
Yeah, so this is good, right? So the region which is in the bulk space light separated from N tilde hits the singularity, right?
Right.
So that's sort of, but fine. Okay, let's not think about the bulk because singularity is confusing. Okay, let's think about the boundary commutant of N. So N is an algebra and it should have a commutant, right?
Yeah, right.
And sort of one safe thing we can say about the commutant of N is that it must include the commutant of M. It has to be bigger, right?
Yeah.
So the commutant of M is just the whole left-hand side.
That's right.
So it is something bigger than all of the left-hand side.
That's right.
So what can such an object be? Like it seems, if we think that left and right is everything, then it seems like the N prime, the commutant, should involve operators from the right.
Yeah, so it's indeed from the boundary point of view, it's a little bit tricky. So it should include all the right operators.
All the left.
Yeah, all the left operators. But also you can imagine there's some superposition of the left and the right operators may also commute with them. And indeed, that would be corresponding to this, from the Bach picture, that's corresponding to those parts inside the horizon.
So you said the extra operators might be some superpositions of left and right.
That's right.
Some linear combinations of these.
Yeah. Yeah, but to characterize them precisely from the boundary point of view is difficult. Yeah.
So why not the complement of N on the right also, the bottom part?
Sorry, say it again.
I mean, why doesn't the commutant include the bottom part of the right boundary? The commutant of the complement of N on the right boundary.
Or if you just look at the operator in the bottom part, they don't necessarily commute with the operator there. So if you calculate because they're if you calculate the commuters, they're not necessarily zero. So you have to construct something more subtle. Yeah.
So this is even in the large N limit, even in the single trace sector.
Yeah.
So Hong, can't we think of those operators as left moving operators from the region below the N where we start N?
Sorry, say it again.
So the extra operators, can't we think of them as, so we have a white region in the right, we have a white region which is not part of N, N tilde. So so there, if we decompose the modes, we will have some left moving modes and right moving modes. So these extra operators, can't we think of them as the left moving modes, which will go into the horizon, and in the end, combined with the right moving modes from the left region, we would be able to construct the operators.
Yeah. So I think that those operators, they in principle causally connected with N tilde. So to construct operator to commute them is not obvious. But if you draw this night cone in the Bach, so as Raghu was saying earlier, so let's just draw this night cone, and then the commutant would corresponding to the operator in this region. So including the full left region, and then the part inside the horizon. So the part inside the horizon should corresponding to some superposition of the left and the right operators.
Yeah.
And including the part you said will corresponding to this white region. in the right, but cannot be fully in the right. So in the right, because it's causally connected with n tilde, so that commuted is non-zero. But somehow you can introduce some operator on the left, somehow to cancel that. Yeah, I don't know. Somehow some kind of combination. Yeah.
Okay, thank you.
Okay, thanks for the comment. Thanks.
Yeah.
Yeah. Hong, just one more last very simple question. Okay, I understand seeing the singularity might be subtle, but from what you described about how the commutators of left and right operators, say after action with this U of S, how they change, is the following correct? Let's throw a lump of matter from the left-hand side, which goes into the forward region, and then construct a suitably translated operator, translated with this U of S, from the right-hand side, so that it goes inside, then you will be able to see this lump, right? From the right-hand side. That's what you're saying, right?
Right.
Yeah, so that's a pretty clear diagnosis.
Yeah.
I see.
Yeah, so the best way to think about it is just you think you have initial, imagine you have initial slice t equal to 0. On these two initial slices, you have some lump of the U here, some lump on the left-hand side, some lump on the right-hand side. And now I just evolve it using some kind of global time, evolve them forwards, and for the whole Cauchy slice. And just like what you do for Minkowski space-time, and then in principle they can meet inside the horizon. Then you can talk about scattering, etc. Yeah, it's just of course the difficulty here is that in the end everything stops at the singularity. We cannot really define an S matrix here. Yeah.
Okay, thank you very much.
Hong, I have just one question about this island thing, whether your construction sheds some light on the island stuff. In particular, so as we know in the eternal black hole construction, there is a particular time at which this island starts, becoming the it shows up.
Right.
Whether that time has any relation to your no, I don't know how to say this, but whether your construction says anything about the island.
Yeah. So the island. So I think it should say something about the island, but it's not so direct. In the sense that this, I think this picture gives us a new way to think about this entanglement wedge reconstruction. So you said we should think about entanglement wedge reconstruction from the operator algebraic perspective, and so I believe that perspective will have should give you some new insights for the existence of islands. And I think this is a very interesting question, but I think it's not so direct. Yeah, just say the connection requires some investigation. Is not direct. It's not immediately from what we have here.
Okay, thank you.
Yeah, but I think it's a very important future question. Yeah, because this whole approach tells us somehow this operator algebraic way to think about the entanglement wedge construction is actually a better way. Yeah.
Great.
Okay, if there are no further questions, let's thank Hong again.
Yeah, thank you.
Okay.